work.
Let's see. It says it's streaming now.
Yeah, it was died.
Try to get the sign up form off if you have that. Sign up? Oh, yeah. I'll do that soon. Just making sure I can.
Yeah, it's on.
Can you just check the quality? Is it 60 FPS?
Yeah.
Oh, it's. Okay. Yeah. Oh, wait. I need to just check if this. Recording. Okay. Sound's working. I'm gonna plug this in too. So guys, if you could just sign in with that link, that'd be great. It also has a link to the workshop or worksheet.
Let me get mine.
Oh, I'm already streaming though. Okay. Hold on 1 second. Just closing everything. Okay.
It's Justin.
You promised me.
Hey.
Are you ordering it right now? Oh, it's fine.
Don't touch that, yeah. Stay on that one.
Alright.
Should I not play the video?
What?
Should I not play the video?
No, you can play it. The first 5 minutes.
After this, though?
We'll leave it up for a while. And then show it right after the 5 minutes. And then start.
Alright. Good turnout.
Yeah.
So far, yeah. Do you wanna, Cheers. Do you wanna stand here while I present or not?
I'll be here.
Alright, cool. Perfect. Good. Alright, I'm gonna play the video.
Sure, go ahead.
For decades, progress in AI has been measured by how well we've succeeded in playing the games that humans play. We've already created systems that can learn to master chess and Go, and many people view StarCraft as the next grand challenge for the AI community. A couple of months ago, we made an explicit choice to try and scale up and speed up the StarCraft project. The way we went about that was to have different versions of the agent compete against each other on something we call the AlphaStar League. This one learning to beat that one, this one learning to beat that one. And that leads them to improve rapidly over time and discover new strategies.
The way it played, you could see it was getting it. StarCraft has imperfect information and is played in real time. It also requires long-term planning and the ability to choose what action to take from millions and millions of possibilities. Look at Danny, he looks nervous. We were able to beat Danny, the best DeepMind StarCraft 2 player. That definitely exceeded expectations.
The next step is we're going to book in a pro to play. I think there's nothing better than, you know, big external tests like that to focus the mind.
If they can already beat me, that would be incredible.
I really thought TLO would, beat us.
No matter what happens, just well done. It's been amazing progress, really amazing.
Our goal is not just to defeat these players. Our goal is to do it in the right way.
Good. I'm a little nervous because
unlike a human player, AlphaStar can see the whole map at once. But we spoke with TLO and created as level a playing field as is currently possible.
In particular, AlphaStar can't react quicker than a human player can, nor can it execute more actions, clicks per minute, than a human player.
All right, 2 seconds, guys.
I haven't really seen a pro play StarCraft up close. The 800 clicks per minute. I don't understand how you can even click 800 times, let alone doing 800 useful clicks.
After the first match, I knew now it was on. That I actually have to work pretty hard to beat this thing. I didn't want to lose.
Incredibly, the system held on.
I was surprised how strong the agent was. I actually lost every single 5 matches.
Did you enjoy it?
I did enjoy it.
Yeah.
Hey guys. Hopefully I'll get to have a rematch where I get to play my strongest race. Well, then I think I would beat it. Yeah.
TLO is an amazing player, but he plays Zerg and our agents play Protoss for now.
With TLO, there was still that but at the end of it, but he's a Zerg player, and so now we've addressed that but.
I guess they need a Protoss specialist, and that's why I'm here. I'm hoping for a 5-0, not to lose any games, but I think the realistic goal would be 4-1 in my favor.
I think he looks more confident than TLO. TLO was quite nervous before. The room was much more tense this time. Really didn't know what to expect.
He's been playing StarCraft pretty much since he's 5.
I wasn't expecting the AI to be that good. Everything that you did was proper, it was calculated and it was done well. I thought I'm learning something. Yes! It's much better than I expected. I would consider myself a good player, right? But I lost every single one of my games.
We're way ahead of what I thought we were doing given where we were 2 months ago. Just trying to digest it all actually, but it's very, very cool. I think that progress has been unprecedented.
It's humbling knowing how many people are working on this project with StarCraft 2, some of the top minds of the world.
These complexities are important to us because they're representative of something bigger. They're representative of challenges that face the whole of AI, which haven't yet been solved.
I think everybody's just very excited to see what comes out of this, and hopefully that StarCraft is going to be a part of history when it comes to AI.
Alright, welcome everybody to BMIC's Intro to Deep Learning workshop. So,
At the beginning.
yeah. So first off, you could just log in with this link real quick. Just so you know your attendance.
And also it has the links to the worksheet that we'll present later.
Is it presenting right now? Yeah, it's supposed to show that? Okay. I don't know why it's doing that. So, this is the Intro to Deep Learning workshop, and it's with me, Darcy, Jennifer, and Julius, so we'll all be presenting different parts of this presentation. And so, yeah, this is BMIC. So first off, it's important to get a definition of what deep learning is. And so, basically, it is just a subfield of traditional machine learning. So it's branched off of that. As shown in the diagram, there's an umbrella of artificial intelligence, which has machine learning in it, which then has deep learning. So it's a subfield of those two. And so it was inspired by the structure and function of the brain, the human brain. And so that's why we call it an artificial neural network. And yeah, it's the basis for recent advances in artificial intelligence. And yeah. So some motivation for deep learning, why should we do it, or what does it do for us? A good example is Tesla in identifying objects and things on the road, such as pedestrians, bicyclists, cars, the road. And so it also brings up an important conversation of the ethics of machine learning, deep learning, and AI, because Tesla recently got in trouble about a year ago for killing somebody because their AI vision was just like wasn't working correctly. But then that also brings the debate of like whether human drivers are better than a computer driver, because humans are also known to kill people while driving as well. So it brings ethics into play. Another example is text generation. A deep learning algorithm was able to create a new Shakespearean piece just based off of reading old Shakespearean pieces. So it was trained just by reading those pieces and eventually made its own new one. Just off of the old works he made. And another example is image recognition. A computer is able to tell what you input, what's on a picture you input, such as a picture of a dog or a car. What is that? And the computer will tell you what it is. So it's pretty impressive what it can do. And also Facebook photo tagging. If you ever get that weird Facebook notification where, oh, I think you're in a picture, and it has like the square around your face, that's Facebook automatically finding like who you are based off your profile pictures and what other people tagged you in. So Facebook kind of knows what you look like in a sense, in a creepy sense too. And there's also many more ways deep learning can be used. And so, as the video that was played earlier, Google AlphaStar, it is a deep learning algorithm that learned how to play the game StarCraft. And it got so good off of its training by playing itself and different models of itself that it was able to beat 2 or 3 professionals 5-0 both times. So they had no chance against it. It was so good at the game. And so it's really interesting because it actually destroyed professionals at what it was doing. So it became so good that they had no chance. Yeah. So what is deep learning? It's a subset of machine learning, as said before. Machine learning and deep learning, although both deal with data, deep learning is very good at handling with larger amounts of data. So based on the graph, machine learning, it kind of plateaus with its performance as the amount of data gets larger, whereas deep learning, the performance gets higher and higher. It scales with the amount of data, so it actually runs just as fine with the amount of data and the performance. And so deep learning, I don't know if you guys noticed, but the price of GPUs has been skyrocketing and falling a lot just based off people wanting to buy them to train neural networks. So the new NVIDIA RTX 2080s have like a special built-in functions just for neural network training. So it's coming to the point where computer systems have their own hardware just meant for neural network training, and we'll probably see a lot more of that in the future. So another way to classify machine learning versus deep learning is in machine learning you have four main things where you input something such as a picture, and then feature extraction, which the programmer would determine the features of a picture, we could say, and then the classification contains of the neural net part, which handles all of the calculations and weights, and then the output, or what it would say the picture is of. But in deep learning, you have the input, the picture, and then it does all the feature extraction for you. So it's actually easier to program in deep learning in some ways, and it also trains off a lot more data. So when it comes to programming a neural network and image classification, deep learning is very helpful because it does the feature extraction for you and the classification in one neural network, rather than in regular traditional machine learning you have to manually point out the feature extraction.
Can I ask about how do you do the feature extraction in the deep learning when you construct the node? Is each node open a feature, or? It
automatically does it.
Yeah, each layer will typically learn some kind of features of an image. For example, if you had an image, the lower level layers of the neural network will learn like edges, lines, and so low level features of the image. And then the higher layers of the neural network will learn, it's like this is the shape of a car and that's the shape of a person. And so that way you don't have to like do manual feature extraction, like actually like define where are the edges or and stuff like that.
So it depends on how many layers you define in the first place that will kind of decide how many features or how complex those features are going to be.
Yeah, exactly. And so I'll show an example of that actually in a few slides, but here's just another image explaining the difference. The top one is machine learning, the bottom one is more deep learning, where it has the feature learning and classifier, the feature extractions, all in one whole neural network, whereas the top one is more separate. And so on this slide, let's say you're trying to train a machine learning network to classify if a picture you enter is of a dog. So you input the picture, and then manually you identify the points of the picture of what signify if it's a dog or not. So let's say the ears or nose or legs, which identify if it's a dog. And then you go through the machine learning network, and then going through all the weights and nodes, and then at the end it'll tell you what the picture is of. So dog, boy, or something else random. But with deep learning, instead of you having to pinpoint each feature, such as like the ears or nose, deep learning will do that for you based on the images you enter. So it trains itself with the feature extraction, which is helpful, and it saves you time as the programmer. Yeah.
Sorry, just to follow up, I still want to clarify on this. Do we actually know that the neural network is learning as human as we learn, as if, for example, when we see a dog, we know it's a dog because of his eyes, because of his nose, because of his ears, but does neural network do that the same way as, because that's the impression that you just gave me. If you said machine learning is actually learning the ear, the parts of the dog, is that actually what it's doing, or is just learning some complex or abstract features?
In a sense, it might be similar to how we learn, but I wouldn't say it's exactly how we learn, because also it just depends on what's our neural structure in our brain. It's definitely different from how we have this, for example, convolutional neural network is what we usually use for images, but our brain doesn't work like convolutional neural networks. So our brain might have different parts that like automatically take the features from a small image, like the edges and stuff, but it wouldn't be the same architecture as a neural network. The neural network is just like a more generalized form, so that it can learn things without having to have specific like groups of neurons that specialize in doing something.
You can also do things like saliency maps, so you'd be able to test like a network what you're actually observing, and be able to see what in an image the neural network is actually looking at, what determines is important for its prediction.
But quite because based on my experience, quite often what we see is just those abstract, for example, like horizontal lines or like oblique lines, whatnot. That things that we don't quite make sense as human, right? So I guess my question is, the question I have just now is, are they actually learning those parts, or they are learning some in some abstract way that we don't actually understand?
Yes and no. So there's an old paper by Oshon and Fields. They're psychology and neuroscience professors from Cornell, and they're studying the visual cortex of some mammals, and that's actually where some ideas of convolution come from. And they actually visualize some of the features that learn from biological neurons, and they're quite similar. So this is kind of why it's important to, at least in our model as well, why we're interested in things like sparsity or other particular features that you find that are that occur in these convolutional features. And so if you actually visualize some of the earlier layers of convolutional neural network, you'll find things like edge detectors or curve detectors. And that's really similar to actually what occurs in the earlier parts of our visual cortex. In terms of the abstract things, in terms of what we learn, they're not learning exactly the same way we do. And so this is kind of why, like Benjamin was saying, if you look at some of the saliency maps in what they're actually paying attention to, sometimes they pay attention to really stupid things that actually don't matter at all. There's this funny presentation from this German professor last year at Mind, Brains, and Machines, and he was saying how there's a particular, they're talking about interpretability, and there's like this picture of like a horse, and it was memorizing the water marker in the bottom left corner to know horse, but it didn't actually know what horse was. But they only found that from looking at sensing that. And then he made a stupid joke about horsing around. And so they memorize these kind of like funny features. And you have like an abstract notion of what these objects are, but semantically they're just patterns to it. It's not like, I understand what a horse is, I understand all the complexity of a horse, and that has, it eats this and behaves in this particular way. But just particular patterns of what represents a horse, topically.
All right. So, history of deep learning. Pretty much what you need to know is that back then people thought of the ideas, but they didn't really have, or the methods on how to make a neural network or train one, but they didn't really have the ways of doing it. They didn't have the computational power or the data sets, let's say. So, yeah. And until around 2006, a neural network, one of the first ones that worked, a deep learning neural network, was created called AlexNet. And so AlexNet was designed by a former Google employee. So he was actually working on neural networks at Google, and then he left to research it on his own. And so it was a convolutional neural network, which we talked about earlier, which specializes in identifying images and working with images in general, so detecting what's in an image like a dog or a car. And yeah, so it had a large impact on deep learning because it actually accelerated the use of convolutional neural networks. It inspired other people to use them and work with them. And it's used so much, it was cited over 30,000 times in other research papers and neural network projects. So it's pretty influential to machine learning and deep learning, even today. And so this kind of goes into the fact of what's making up a neural network. So there's nodes and weights, and we'll get into that. But pretty much comparing it to a biological human brain, we have neurons, which contain information and are connected to other neurons, which they just hold information, they tell the other ones what to do. And comparing that to an activation, which is a node or neuron in a machine learning algorithm or neural network. It has information, and these lines going into it are called, what did you say, the dendrites in a human one? those lines are like the dendrites in a human one. So those are also called weights. And so, yeah. And so all of these make up a neural network. So they're all built off of activations, as you call it. So these are neurons in a human biological one. Those are activations in a neural net. And so what is a neural network? Typically, a neural network has 3 types of nodes or activations. There's an input layer, which contains everything you input. Hidden layers, which do all the calculations, and they're all connected by weights. So those lines are the weights, or the dendrites, as seen in this slide. And then the last layer is the output layer, which actually tells you what the input and hidden layers are trying to find to do, or what are they outputting, what is the user inputting, and what do they want from the output. And so a difference between a deep learning neural network and machine learning neural network is that deep learning neural networks typically have more hidden layers, as seen in there, whereas a simple neural network won't have as many. So, yeah. And so the steps to training a neural network, or a deep learning neural network specifically, is forward propagation. So let's say you put something in an input node. It passes it through the entire network and gets the output, and then compute the cost, so calculate how off is the specific output you have. So after forward propagating, you have an output that shows how wrong it is from the right answer. And then backward propagation goes back 1 layer, and it tells the nodes, oh, this was wrong by this much, fix it. And then the previous layer then gets fixed from the forward layer, and I'll show you that in the next slide. So those are the 3 steps though: forward propagation, computing the costs, and then backward propagation. And so an example of this would be training a neural network to find the house of a price. So this will probably be easier to understand with an example. So let's say you have a house and you're computing the cost based off 3 inputs: the number of bedrooms in the house, the number of bathrooms, and the square feet of the house. And so those inputs would get pushed through the hidden layers, and the output would be the total price of the house. And then there will be you would compare the price of the house to the actual price, so it would know it's correct through the training. And then you would go back through the hidden layers to fix those weights and nodes based on how off it was. And that's through forward propagation, computing the cost, and backward propagation. And so yeah, this then leads to the next part of the presentation of regression, and yeah.
Hi, I'm Jennifer, and I'm going to explain how we can start building up this neural network. So now let's start by looking at how to build a single neuron. So we all know what a linear regression is. It's a simple y equals mx plus b. Let's look at an example. Say you want to predict the house prices given some features of the house. So the x inputs are the parameters, and then to represent that in an equation, we can have it to be z equals 5, the input parameter, times certain weight, plus 3 times certain weight, plus 3,000 times certain weight, and then plus the bias. So this is the linear regression. But then this is too simple, right? So now we're going to look at logistic regression. It's almost like the linear regression, where it has the linear combination and it is made up of the weights and a bias, but it is fed through an activation function, such as a sigmoid function shown here. And we're going to talk about what an activation function is later in the presentation. Okay, sorry. Let's look at an example. So now say you want to determine whether or not you could afford the house, rather than calculating the cost. In order to do that, we could use something called the activation function called sigmoid function to make the output values to be between 0 and 1. So this can serve as a matrix of how affordable the house is. So now we just learned how to build a single neuron, and we can put all the neurons together to build a neural network. So let's look at shallow neural network where we have one hidden layer. So now we're going to add more activations as shown in the diagram there, which results in a hidden layer. So each activation takes in an input from the previous layer, and that's going to occur in every single one of the layers. And adding another layer means that we can learn more complicated functions as we go on.
So basically, as you can see, that one circle represents one activation, right? So one activation in the hidden layer, say that blue node on the top, that has inputs from the input, so 3 of them. And basically, all it does is it takes those numerical values and multiplies it by some kind of weight. And then you add it to the numerical value for the second input, add it times the weight, third times the weight, and then add a bias, and then you take that whole term and you put it through your activation function. Now the activation function squeezes it between 0 and 1, for example. So that's an activation. So we can just say if it's close to 1, we're saying that the activation is on, or the neuron is turned on. But if it's close to 0, then the activation is off. So it's turned off. Okay.
So let's look at an example. Say you want to predict whether or not it's worth going to class or not. So X will be the input parameters, which could be things like difficulty of the material, number of assignments that are due that day, and days till midterm. And Y would be the output, which will be the probability of you actually going to that class. So if we look here, the first equation would be the equation for the first layer. So sorry. Okay. Yeah, so the first equation is for the first layer, and then you take that and then also do that to the second layer. And then important thing is that we take the weighted sum and then put it through the activation function to make sure that the values are between 0 and 1 in this situation. But again, there are many different types of activation functions, which we'll look at now. So there are 3...
sorry, I have a question. Can you go back?
Yep.
So in that X matrix, you have those 3 are features, right?
Yep.
I thought the feature is going to be automatically selected.
Well, those would be like features, things that respond to like the pixels in terms of an image.
So it is able to do that, but I can also specify my own features.
Just like if we take like the housing example, you just pick like, okay, we think that a bedroom, or number of bedrooms, number of bathrooms, square footage, that would be what goes in. And then it would decide which one was important. And then with images, that's where that your feature extraction really comes play. It figures out which one of these pixels is which virtual pixel is.
Okay, so if we come back to this example, we have 3 features. Let's say we have 100 samples. Right? So we have, that makes sense, right? 100 samples, 3 features. So each sample for each feature is going to fit one of those 3 circles in the first layer, the red circles. So, or how I'm going to, because I saw this matrix multiplication W1 times Xi. What does that Xi mean? Is it a vector or?
We're not doing any vectors right now, just vectors.
Okay.
Yeah, so each Xi, just to recall, is just the feature itself.
So X1 is just difficulty of material as a scalar value. X2 is number of assignments due.
Okay. So I suppose, for example, if we have 2 students in this case, we have 2 values for difficult material, so that will be a kind of a 2-member vector to be put into X1.
Oh, so we're talking about sample size on this.
Yeah.
So basically, it's an iterative process. So we're going to go down the line, but you're going to do 1 image at a time. In this instance, so X1 is X2 is going to represent the first sample. The next iteration is going to represent the second sample.
Okay. Okay. Thank you.
Okay, so going back, let's look at activation functions. So sigmoid function causes the outputs to be between 0 and 1, as shown here. And tan H causes the outputs to be between -1 and 1, and ReLU causes the outputs to be outputs to come out to be positive real numbers. Now you may ask, why do we need to use activation functions? It's actually really important because if we don't use activation functions, then the algorithm that we call on will be just linear activation functions. So it's like the simple y equals mx plus b. And we don't want that because while it is simple to solve, that lacks the complexity that we need to train our neural network. So linear activation function will output, again, linear activations. And for example, you might use linear activation function in one place in the output layer if the output is real numbers. But even in this case, if the output value is non-negative, then you could use ReLU to make it positive. Now, why do we need non-linear activation function? This is because there's this problem called XOR problem, which states that there is no way to correctly classify all inputs with a linear decision boundary. So if we look at here, we use the linear classifier to attempt to separate the red dots from the blue dots. And there's an infinite possibility of linear decision boundaries that you could draw, like a single line. But as you can see, there is no way to separate them with a single line. But if we look at the diagram on the right, using two-layer neural network with sigmoid activation, you could actually separate them out. And you might ask, why do we have two lines there? It's actually not. They're actually not two separate lines. They're just planes overlapping on top of each other. So if we look at it from one perspective, that looks like it's that draws two lines on a single plane. So now we're going to look at forward propagation. So we've seen neural nets with one pass-through, but normally we're going to have multiple samples. So one way to do this is do it in an iteration. Now this is really inefficient, but this is one of the simplest way to do it. So let's look at it. So for each activation J, so one of the activation like the circles, and for each of the layers, the activations stacked on top of each other, and for the sample size I, we're going to put it through this equation and then finally compute the cost to see how accurate our neural net was. So computing the cost is really important because in order to train our neural network, we need to know how far off our estimate was from the actual value. So we defined the cost function by using j of y hat, which is the value that we get, and then y, which is the expected value, as the sum of the losses. And here, the losses are the error for the single training example, and the cost is the sum of all the losses. And then we used all that to train our neural net with gradient descent. And we're going to get to what it is in the later part of the slide. So let's look at an example of forward propagation. So the basic equation is shown above, like z1 subscript 1 superscript 1 is equal to the weight times the inputs. And basically, the subscript is the number of the nodes, and then the superscript is representing the layer. So the first equation has superscript of 1 because we're only looking at this input layer right now. Sorry, the first hidden layer right now. Here. So we're gonna let's do this out. So we're gonna multiply the first activation with some weight, which happens to be 0.5 here in the example. Add that to the second activation times its weight, 0.1 times 2, and then add that with, again, the activation times its weight, which is 0.0058. And then also add that with the bias that we're going to give, which comes out to be 0.7. Now, as we talked about before, if we just do this, that comes out to be linear. So we're going to feed that through the activation function, which we're going to use ReLU for, which comes out to be 0.7 again, because again, ReLU is just turning all the values to positive, real values.
So where did the weights come from?
So weights are stored in the neural network. For each activation, the activation has a set of weights. So each individual activation has a different set of weights. It can be different from the 3 other neurons that we're not going over right now. So we just went over the first neuron right there, and that has 3 different weights. Also the second, third, and fourth also have their own set of weights, which could be different numbers that you see up there. And that's why they also have different numbers, 0.2, 0.3, 0.9.
Also, upon initializing the neural network, the weights are all random, so it can be across like a uniform distribution or something. So the actual initialization will find a few weights over time.
And then we're going to do it to the second layer as well. I mean, which is the final output activation. So then we get y hat, our value, to come out to be 0.45.
And notice that y hat, the predicted output, is equal to A2, which is the second layer in the neural network.
And then we can compare that to the actual value, which was supposed to be 1. So now we need to compute the cost, compute the loss. So put it through the L of y hat and y.
So we're just computing the error right here to see how good or bad.
The single error, which comes out to be 0.798508. Now, what does this mean? We can go back to the very first example, the second example I talked about whether you want to go to, it's worth going to class or not. So, if you look at this diagram that we've been looking at for forward propagation, this is the same exact diagram. So, we said our y hat, the probability of going to class, comes out to be 0.45. So if you look at the conditional statement there, we said if our y is greater than 0.5, then we're going to go to class, or else we're going to skip. So in this case, because our y hat value is less than 0.5, we're going to skip the class, right? But then it turns out that the professor covered the midterm material during the class. Oh no, what happened? This is because our mistake came out to be 0.798508, which is closer to 1 than 0, and that means that our neural network was not that accurate.
Is the loss function has any boundary between 0 and 1, or it can be any value?
It can be any value, and it depends on what loss function you use. So loss functions can range, like, there's many different loss functions you can choose from. Like mean squared error is a loss function, where you just take the difference and then square it. And that's a very simple loss function. Another complicated loss function could involve loss or logs, like what we've shown before. But I wrote this down because this is like heavily used in machine learning, to reasons we'll get later. But it makes the training process more easier, essentially.
But essentially, in this case, we don't really know if, for example, if the loss is 0.7, we wouldn't be able to know if it is a good prediction or not. Essentially, what we're doing is just try to minimize the loss function.
Yes.
There's no boundary to the loss.
If we're given some kind of numerical value, we don't know explicitly what that value means until we compare it to other values. So just in general, the lower the value, the better it is.
Additionally, during training, there's a metric called accuracy that we tend to use. So that might be discussed later. Basically, you'll like compare what you actually got against a bunch of stuff. You'll get like percentage of how many you actually got right, how your accuracy is. That's I think how well.
Yeah, that feels more.
Yeah. The reason why we don't use that for training is because with gradient descent, we need some kind of error to backpropagate, and that involves taking the derivative and stuff. So we can't take the derivative with accuracy, for example. All right. So that's how you basically have a network go in a feed-forward fashion, just having from an input and you feed it forward through the network, and then you generate some kind of output, and then once you get that output, you compute the cost, which is getting the error of that output. But now we want to think about how do we use that cost and make our neural network predictions more better in the future. So first of all, let's talk about some terminology. So we have parameters and hyperparameters. So basically, parameters are anything that is learnable throughout your training process. And those can be your weights and your biases. So those are all stored within your neural network, and for each activation, it's different. Now you have hyperparameters, and these we'll get to in the near future, which is like the learning rate, and you set those manually before you train the neural network. Okay, so let's revisit the cost function. So the cost function is the sum of losses for all training examples, and basically you just have one loss function and you get some numerical value, and then you iterate over all of the training samples in your data set, and then you sum them up, and that's what your cost function is. And the general form for writing a cost function is j of theta. And what theta means is all of your parameters for your neural network, all the things that are learnable, so the weights and biases. They're not the hyperparameters. So they can always change over time, meaning your cost function, what you get as a result, always changes. Right. So I'm going to give a brief summary of gradient descent, and then I'll go into the details of how it works. So our goal is we want to change all of the weights so that our predictions fit the data better. So do you guys understand what that means so far? All right. So now how we're going to do that is we get the error between our predicted values and the actual values, and that tells us how much we need to change each individual weight. So either increase or decrease the weight, and that will result in some small change in your network. And how do we actually do that is by calculating the derivative from the cost function, and then we get a numerical value of change that we need to do. So that's basically the definition of a derivative. It's some kind of change. Now, the derivative is equivalent to the slope at one point. So, and that tells us where the error is to be minimized. So I'll show you a visual example of what that means. All right, so here is like a visual example of the cost function. It shows us where the error is high and where the error is low. So in general, we want our model to have a low error, meaning that the predictions will closely match the actual values. And so here are like two different local minima that that the neural network might want to go to because the error is low. So throughout the gradient descent process, we start at one point, and then we say, where is the error changing towards to? Where is this slope of steepest descent? So we're only able to see what in one place where we are. We can't see anything else around us. So a metaphor would be like you're walking down a mountain blindfolded, or you have a ball and you set it at one point and it rolls down a hill. So we look at this one point and we say, where is the slope of steepest descent? Well, to find the slope, we compute the gradient or the derivative. So how do we get the gradient or derivative for one parameter? And how do we change that? So what we do is we can take a cross-section of what the gradient is, and then we say, okay, for this parameter, when we change it along this axis, we can see that the error tends to be lower on this point right here. So at this point, we take the derivative at this with respect to one variable. So that's the partial derivative, which means you're just fixing everything else except for one parameter, and you say, with only this parameter, which way is the slope of steepest descent? And that is this. So this is the derivative right here, and we just say the derivative of the cross function equals to that. And then we go on to the next example. And then, so we have a different parameter. This is parameter 0, this is parameter 1. And then we say, oh, what is the derivative at this point? Well, our model turned out that the cost function gave us an error at this point, this high. And then our parameter setting was at this position. But now it's saying that our derivative is this way because we want to increase our parameter value to this value right here. And so by getting that, we can do this iterative update process. So at each step, we go some small amount, and then we get closer and closer to the local minimum, or sometimes global minimum in this cost function. Okay. So here is the equation behind gradient descent. So we have the one weight. So theta j is one parameter. This can be your weight or bias, remember. And then we have our learning rate that tells us how fast do we want to change our parameter. And usually the learning rate is set to something like 0.001. And now we have this derivative, and this is just telling us where is the slope. What direction do we need to change our parameters in? And yeah. So any questions so far about this? Good? All right. So now we're going to change up and think about how it works with neural networks. So our goal is to update the weights and biases of each neuron, and then such that the cost function will output a smaller value after we run this again, for example. And so the difference between the actual and predicted values will be minimized. So we want to repeat this process for many iterations. This can be also another hyperparameter you set. So this can be like 1,000,000 times. You just update it, say. And so you compute the forward cost and forward pass, and then get the cost function j. So we put it through our model. We multiply it through those kind of weighted sums, and then we get the output, and that we get the cost function between the that's the difference, right? So with that difference, we say, okay, now for each parameter, how much do we need to change it? So W1, that corresponds to all the weights for this first layer. B1 is also the biases for this first layer. W2 is the weights for the second layer. B2 is the weights for also the biases for this second layer. Okay? So basically we have the same equation.
I think I missed it. What's a bias?
Bias? Okay, so when you have a weighted sum, right? You have, say, this first neuron. You multiply x1 times a weight, x2 times a weight, x3 times a weight. So you sum that all up, and then you sum it plus a bias. So the reason why we add this bias is because, like in linear regression, you don't want to start from the origin all the time. You want to start from somewhere up because the data might not be always originating from the origin. So it's like that kind of concept applies to neural networks. And so that's why you have bias too. And so we want to do this equations, but we already know what these weights are. We know what the biases are. But how do we find the derivatives now? So that's a question that we'll use calculus for. And so to compute those derivatives, we use the chain rule. And from calculus, you might have heard of chain rule. It's basically a way to compute the derivative of functions of functions. So as you can see up here, you have the derivative of f of g of x, and then that's equal to the derivative of f of x with
with g of x inside it, and then the derivative of g of x. Okay. So how do we apply that concept to neural networks? Well, we just think about the structure of a neural network. So a neural network is kind of like functions of functions, because when you have the input in the beginning, it goes through a weighted sum, right? And then you get one activation. So that process is like a function, because you get from input to activation in like some kind of functional process. Now, at the second layer, you have these bunch of activations that are also passed into a feed-forward type of thing, where you have the linear combination or weighted sum, and then you get this last output, which is a weighted sum. And remember, you also have the functions of the activation function at each step. So that's also another function you have to apply the recursive chain rule to. So as you can see here in this example, we want to get the second derivative. We want to get the derivative for the second layer weight. And so we take the derivative of the cost function with respect to that weight, and that's equal to this. So the derivative of the cost with respect to A2, that's the second activation. Then we want to take the derivative of the activation function itself, and that's A with respect to Z. And then after we take the derivative of the activation function, then we want to take the derivative of Z, which was the weighted sum. And then once we get the derivative of the weighted sum, we get derivative of W. So as you can see, when you multiply this out, you also just cancel out these. So that's why you get J with respect to W. And then we can do that same process for weight in the first layer. And then we just repeatedly do that again. Yeah?
So for this example, we have 3 weights, right? Because we have 3 features, so we have 3 weights. And just now you mentioned that for each node, for example, in the first layer, for each node we have 1 set of weight. Right? So for example, in the first, I'm not right to say that.
So actually, I'm going to ignore like what the dimensions are and stuff right now, because this is for like a whole neural network and like all the training samples and stuff. I'm just going over this to like cover the concept, and then I'll go into the specific dimensions later, because I'm gonna do this process called vectorization, and that will formalize all of the dimensions. Okay. All right, so this is like the equations, and I'll just show you intuitively how to get those chain rules, but I don't actually like get intimidated by like what the derivatives is, because we have software that already computes the derivatives for you, and so all you need to know is just what are the equations for forward propagation, not back propagation. So you don't have to take the derivatives from yourself usually, but let's just see how the train rule applies. So we have the cost function, and then the cost function is a loss function, or a sum of loss functions. So that's another one step of the chain rule, that we have to take the derivative of the cost function with respect to the loss function. Now in the loss function, we have y, which is y hat, which is the second activation, and that's also another equation that you plug into, and then you like it's like another function that you apply the chain rule to, and so this keeps on repeating to get z, a1, and then z1, and then finally w. So as you can see, this is just like a way to see how a neural network is functions of functions. Okay. So now that we've covered up like what gradient descent is in a high-level form, let's go into like the low-level details of how these matrices and vectors apply to neural networks. And the reason why we kind of want to use this is because we want to speed up our training process. So here is like a visualization of like what modern GPUs do actually with neural networks. So you can see like these multiplication of matrices or tensors, and then Depending on the architectures, it can be faster or slower. But basically, as Darren said earlier in his presentation, we have these GPUs that have these tensor processing units inside them. And that's what like all of hardware is going towards now, is that we have these different kinds of tensor-specific processing units. And what tensors can do is they can store a lot of the weight matrices that you will see in your neural networks. So those are all the parameters that you will learn. And you're always constantly updating those parameters. And so we need like a fast GPU to do that. So anyway, I'll read the slides. So recent models require massive amounts of computational power, and therefore obtaining the most efficiency out of your model is crucial. So linear algebra libraries are becoming more efficient, and neural networks can benefit from this outcome, like the matrix multiplications of NumPy or the tensor operations of TensorFlow, which you might have heard of before if you wanted to get started with programming neural networks. Okay, so very basics. These are vectors and matrices. So as a vector, we have magnitude and direction, and that's like a feature vector, which we had before. These are the values of our features, like difficulty of class, number of assignments, days until midterm, something. And then we have a weight matrix, or just any kind of matrix which stores all of the weights. It's just a way to store things. Okay, so now we have manipulations of vectors and matrices. So we have the inner product, which you'll see is just the weighted sum. And that's like the activation of your neurons. Like you have weights times activations, and that gives you an output. And you add a bias, and then you put that into activation function that gives you the output for one neuron. And so that can be written as just a dot product. So we simplify this greatly by using linear algebra. And I'll show you another example of that. So, and this is a matrix vector multiplication. So then we have a 3 by 3 matrix, we multiply it 3 by 1, and then we get a 3 by 1. And these are all weighted sums. And that's that. And then we have matrix multiplication. So we have 3 by 3 times 3 by 2. And then that gives us the 3 by 2. Okay, so now we're going to take one activation and then we're going to make it more compact. So we have all of these weights and plus a bias. So this is the general case. So the L right there, that's for that specific layer. And then we have weight 1, A1, all the way up to A, weight N, AN. And that's for all of the activations in the previous layer. So for the highlighted neuron, the previous X layer, that's that activation. So there's 3 of them. So it's W1, W2, W3. And so what we can do is we take that and we turn it into a dot product. So we take each weight and then put it into a vector. We take each activation from the previous layer and put it into another vector. And so when we do this operation, we get the same thing that appears on top. And then that equals to one scalar value, and we add the bias, right? So once we get one scalar value, that's the activation. And this we compact into this kind of notation, which is WL transpose times AL minus 1 plus B. And that's equal to ZL. And then we just do the same thing for the activation. Since we already have ZL, and that's a scalar value, we just put it right into the activation function, which could be, remember, ReLU or sigmoid or whatever. Any questions so far? Or am I like boring you to sleep? Good? Okay, you understand it? I don't want to go too fast. Okay. Okay, why isn't that? Okay. All right, so this is an example. We're just taking all of the numbers in here, and then we're going to put it into a vector. So we had that linear combination that we did before with Jennifer's slides, and we're just putting it into these two vectors right here. And then we add the bias and get 0.7. And then we just put it in through ReLU, and that gives it, remember the ReLU function is only positive numbers, so it's the same number, that's why. So now we want to do it across all activations. So let's do it for the first one. Now we have the same equation, W1, layer 1, transpose X times B. And then we get the equation for A1, which is G of Z. Now we do this for the second one. So just a copy of the top one, but just different weights now. And then we do the third one and the fourth one. So these are all of these activations all at the same time. So how do we make this more efficient? By parallelizing it, by putting it into one single operation. Well, we can do this. So we have Z. This whole Z values, which are scalars, can now be condensed into one vector, and then that's also represented at this end right here. Okay. Now we have these. This whole thing we're going to take and then put it down here. So as you can see, it's just the same equation from the top. It's W1 transpose times X plus B1. That's from the top. And then W2 X transpose times B2, and etc. Now, with this, we have one vector, and we can split it across right here. Because this way we can do a simple vector addition. Okay? So now we have the B's separate. But now what do we do with this part? So we can also just take these apart too. So if we have W transpose, we can take that, take it apart, and then we have X here. Because notice X appears in all of those. And X is a vector, right? So a vector multiplied by W gives us some weighted sum. And so what we can do is it's equivalent right here, where we have each X value. We take that, we transpose it, or we can take it and multiply it by each thing. And that will give us this equation here. So we have a transpose weight vector. A transpose weight vector. That's one layer. One row. And we have multiple of them. So now it's a weight matrix.
I guess just to follow up my previous question, I just want to ask, so for example, if you write it like this, and then each W will contain three scalar value in our example, right? So in this case, there will be 12 variables, 12 W for the first layer.
Yeah.
And then when you do the differential, you will have to differentiate the cost function with respect to all 12 of them. Is that?
Yeah.
Okay.
So I'll show you an example later, but I'll show you what the dimensions actually look like for the first hidden layer. Okay, so I just took that equation and put it up here, and then now I want to condense it. So Z for the first layer is just ZL of I, which I denotes the first training, or what Ith training example. That's just one example. So we're not thinking about training examples yet, but we'll get to that later. So, and then we have a weight matrix. So that's that, which we made like a matrix. And then we have the previous input vector, or the previous layer. And then we have a bias vector. And then we have the activation, which is a function of Z, which is a vector. All right, clear on that? Cool. Okay, so a simple naive way would just do these equations and like iterate through all the training examples. So we just have that and we expand it out to all of the layers, and then we just repeatedly do that. Okay, but now we don't want to just do one sample at a time, one data point at a time in our training data. So what we want to do is we want to vectorize across multiple examples. And what we do that is we basically stack different examples on top of each other. So as you can see here, we have different examples stacked on top of each other, and then you can just think about it as the different vectors and matrices adding one more dimension. So instead of having a weight matrix, we have the weight matrix plus another dimension, which is the number of samples you have. Okay. So again, this is a way to iterate through it, right? We have the previous equations, and for each sample, we just iterate through it. And then at the end, we just compute the cost function. Okay.
And just to reiterate, we're going through each sample, each separate different GPU, for example, right?
So yeah. Well, if we just iterate it, we can't use a GPU process because we have to wait until the first training thing is finished, and then we go on to the next one, and then.
Well, I guess I meant more on separate CPUs, or like, you have to wait through sequential.
Oh, well, you could actually like put it on separate CPUs, but you can't use a GPU yet.
Yeah.
But that's why we parallelize it. So here's like what a visual example of what it looks like with the dimensions explicitly for this first layer. So we have the Z, which is 4 by 1, because there's 4 activations. And then we have AL minus 1, which is an X, and that's 3, because there's 3 activations before. And then we have 4 by 3 weight matrix, so that we multiply this against each other, and then we have a 4 by 1 vector, which we add a bias, and the result is Z. And then we take that and then put it through an activation function, and then we get A. And so that's how you get this whole layer in just like one process. But now we want to do it for more examples. So as I said, we just stack everything on top of each other. So we stack all the training examples on top of each other. And as you can see, we have this n dimension right here. This is like the third dimension to it. So as you would call it, it's called tensors, hence TensorFlow. So we have NH. So this is a number. This is the number of activations in a hidden layer. So at this hidden layer, there's 4, because it's 4 right there. And then we have NHL minus 1, which is also this, NH minus 1, which is 3 activations, right? So at this point, we can still do the same kind of multiplication that we've done before, because we only added 1 dimension, but we don't have any interaction between those different dimensions, or interaction between 2 different samples. So basically, we just do the same operation. So if you visualize it, you take this, you put it on top, align it with that, then you do this weight sum. And then you multiply those out, add a bias term, and then you get this first thing right here. It's the same thing for the second row and third row and fourth row. You're just doing the same kind of multiplication with just an extra dimension, but it's not affecting the way you're multiplying things out in any way. So we're going to just use that kind of notation and just simplify this out as here. So now we don't have to have an I for like what a training example is. We just say Z equals W transpose, or W times AL minus 1 plus B. So it turns out to be a simple equation that you can just use. Okay, are we clear on that? Alright, so now we're going to vectorize gradient descent because we didn't talk about gradient descent in that much detail. But now we have to deal with these matrix calculus that because we're computing the derivative of matrices. But actually, in reality, it's not that different because all you're doing is you just think about it per value. So like one entry in a matrix, you just calculate the derivative of that one entry. Well, all you're doing is like you're making it more compact, and so you're doing multiple equations at the same time. So basically, we're going from iteratively changing each weight by the derivative of the cost function to, in parallel, simultaneously changing each weight by the derivative of the cost function. Okay. So previously we had this kind of equation where we had the one parameter, and with that one single parameter we just update it by some kind of derivative times alpha, which is the learning rate. So we're changing it slowly, little by little, per each weight. But we don't want to do that like for every single parameter when we have millions of parameters. We want to do that in parallel with a GPU. Okay, so then we're just going to think about the weight matrices. So we have W at the layer L, and then we have W, and we subtract the gradient, or the derivative of the cost function with respect to this W. Okay? So that gives us simultaneously the derivatives for each parameter in the weight matrix. So in this 3D commodulation, for each different weight, we have an update rule for that single weight. And we just apply it at the same time. Okay, but how do we compute what that derivative is? Of course, that's more involved. The derivative part is probably the hardest part. And so I'm not going to derive it for you, but here are some equations that you can use. So there's different ways to derive it with matrix calculus, but in summary, we don't have to do that because of linear algebra libraries and TensorFlow. So we have this. I'll just show you what the equations are, and we're not going to deal with them until maybe if you want to do the worksheet later. So we have W equals that. Remember, we had our output from the neural network, which was this A2 minus Y, which is our cost function, right? If that's the derivative of the cost function. And then we have all the derivatives for each different weight. And then what we can do is we take this derivative, we literally just plug it into that update rule we had before. We take that derivative and plug it into here. And that gives us what change we have to do with our neural network. So we can do that for every single parameter, and then and also remember, we have to do it sequentially backwards because we're using the chain rule, and so that's why it's back propagation also. And then we have some derivatives for the activation functions, but remember, you don't really have to know this by heart. It's just, you can see that like, for a value, for example, it's just 0, 1. And like, we have 0 here because we're not changing anything, and then 1 here because the slope is 1. And in most cases, we just use value in our activation functions because 1, it's simpler, but 2, it's also that it avoids this this problem of not learning anything when you're on these extreme points. So like when you're on this extreme, like the gradient, the derivative is 0. So when you apply the update rule, it's not going to move anything. So we want like a constant slope. That way it's always 1. So you're always learning something in each iteration. And it turns out that this works fine perfectly without any complex function. The only reason why you would use like a sigmoid activation is when you want something between 0 and 1 at your output. But other than that, you don't really use it. Yeah.
So for the wave function, you still have this horizontal line where the slope is 0, right? So wouldn't that be the same case when you don't learn anything?
Yeah. So it could be that, but it turns out that when you have enough parameters, enough weights, that there's always going to be a slight chance that something here doesn't work, but then something here does work. So it's worth the trade-off by doing this, actually. There's also been proposed solutions where you have something called leaky ReLU. And so it's basically a very small slope here if it goes off to 0. So it does have some gradient that makes it tend towards this way. But in general, this works perfectly fine in your model. Yeah.
I might have missed it, but like, how does adjusting the learning rate like affect gradient descent?
Oh yeah. So actually, I didn't really talk about that. But so if we went to our example, that's a really good question. So like here, if you had something here, and you had like a very high learning rate, so you multiplied this derivative by a very high number, you would just overshoot it completely because you have like a giant learning rate, and then that just goes out. And then so at this point, now you want to go this way, but then you have also a giant learning rate, so then you just overshoot it completely. And so it just goes bounces force and out of it and completely blows up your neural network. So that's why you want to have a small learning rate, is because you want to have it so it doesn't overshoot anything and just converges at this normal. Because this gradient also gets smaller as you go on, so like the derivative gets smaller, so you'll eventually converge. You can't overshoot it by having a small learning rate. But the problem is, again, if you have a super small learning rate, you're not going to move from this point. You're just going to stay because it's so small. So you have to find this balance, and that's a hyperparameter you have to set. So let's see. Yeah. So actually that was it. Great. So we have a part 2 after this, but so in general we have some meetings that you might want to come to. It's a Society and MLI discussion. That's this Tuesday, February 5th. Our first paper discussion is the following week, I believe. And that's Tuesday, February 19th. Or no, is that 2 weeks from then? 2 weeks. And then we have this Google Brain Talk by Sami Benjo that's going to be here. No, not here. It's in the Photonics building. February 4th is Monday. So if you're interested in like machine learning research or more advanced methods, then definitely come to that. It's pretty cool. And you can see like me, like a Googler, and get connections and stuff. So yeah. So now we're gonna work on, actually no, let's take a break. There's some pizza right there. Yeah, there's pizza right there. Let's get some food to eat if you're starving. And then we'll move on to our actual implementation of neural net.
When you go deeper and long, it's still that long. Because this kind of general research really. Just know what you're saying. There's a research paper saying that at early stage, it's like a neural network. I mean, the first result for the first and second is probably the extraction. I'm sure the collagen and waste of that's what you're saying. But then, as we kind of
I didn't even
deeper and deeper information.
What do you mean by
layers?
Okay, so like,
you guys do
so you get to see and it should be like easy to
I think
but that would significantly impact.
So you want to have your neural network like the creatures give you what? Like at these wages, and when you post it on LinkedIn,
I think
well, you still kind of like do its best.
the way that particular features that it's using to
Shop features yeah, you definitely
are different from how we would usually say
like for example, like honestly, 80% of what you
and so
is getting what happened. If you remember,
it's definitely not learning
on the we're doing working on some project and we're trying to think where David is
and so you start to think high level features and you can see that.
so originally how would you start this? We had a bunch of data. We just ran all this stuff. We realized that like you have to I'm actually thinking of Coursera on the bundle Coursera on this thing. That's what I'm saying. That's just a bad.
Yeah, so that's
Octane also
what's your sense? I can. And yeah, so there's a lot of why we don't need concrete.
That's a there's only a version though, so like you can it's like the conclusion, so
because we can always print out the output that each node. But when you, for example, you have some abstract data, I have a bunch of, for example, back your data, whatever. My question is, how are they able to extract why they are thinking certain features are important that we human don't think so? Or can we human make sense of whatever feature that this machine is extracting? So that we appreciate what you're doing.
So during this stuff,
but I guess it's still very hard.
You're right that.
So I went to this whole thing and was like kind of my
the natural structures that should help and so one particular feature in actually is digging some down. And so that's visual feature detectors, and we had certain features together. This weekend,
were you at any point? I apologize.
You don't really get that time. You're just like sometimes whatever else, and you're just creating an arbitrary feature. So there's no competition.
Like I can't fill out your cards for the next like 11 because I don't know what I can plan.
Yeah. So the idea is that you can process.
Yeah. Well, she's like, you have your savings. I want to.
And now you have this one particular
so I need something and then now you're like stop me because I'm my reason it's classic because they're getting like a birthday party is sending it in birthday party mail invitation to every exception at your
yeah, the five. That's mine.
Would you be more time if you got a letter?
I mean, if I can send it so you guys worried about the culture?
No, it's just
So it's 750 though? This would be better for board price.
So little
discussion of that. How to with feature selection. I know about how to for it. We did that.
To an extent, actually. So it's just and that doesn't make sense.
Like you'll be working on a different project, or like active on like vectors that
you can feed in art. And there is still some pre-processing that
I will be around when these are like you will get so I'll text my map
Okay, I know that.
so that way when you're computing
You like apply, but you like legit reason.
Yes. Yeah, so
it's just like
I mean, I like your applications and stuff.
great.
I mean, if you get a bunch of computer, as long as it's not a manual and you're
I took it on yourself. Whoever is hired out doing that. I think it's must be easy to
So I have some microbiome sales pages.
I definitely took some notes on it. Like models require massive amounts of computational power. Obtaining efficiency vectorized algorithm for propagation going from iteratively changing each weight by the derivative of the cost function to, in parallel, simultaneously changing each weight by the derivative of the cost function. So I would say after that,
is it just for citizens?
I did this by ML because I took my ML with business. This is all about linear regression though, so I felt like I had like a good basis for that one slide about linear regression.
So, how is that?
We are doing subset selection class.
Just like hyperlocation.
Maybe least square, maybe diagonal, maybe support vector machine. Yeah, something that's super flexible but low interpretability. Knowing all this, you would be way ahead of the class. I'm doing it like you're not yourself.
When I used to do something,
we're using mean squared error.
Okay, so they can also. Unless you was the
so then the function.
Yeah, that
for example,
it's a simple thing. It's like, me, I know faster.
So that's kind of
so my question is then, if people are so much better than just normal ML, why don't you take out
like immediately there's one guy because for interactive design they just give you
I mean, there might be some problems where it's more
sometimes I read messages in the street all the time. I
guess if you pick up the past,
sometimes I read messages on the street.
Yeah, so
make something out of it.
I don't think there's really
like people are thinking of these apps they want to play and stuff like that. I don't know if you guys are the actors. It seems like about
and there's other
you want me to make the accents for it? I'm actually like learning.
Alright. Did everybody get a chance to input this URL? No?
It was set and also information. So you can think of like the social network there was graph templates are really good at handling this particular geometry type data. So basically,
is already open?
Yeah. And so perhaps like one way you could do it is you would have each vector describing each of the cells that you're looking at. And then
probably
those would each represent
open plate on it.
And then there'd be some kind of relation. And then we can do is
So am I live coding?
If you want, yeah.
Okay.
What were you planning to do?
Oh, I was planning to like do more of a workshop setup so people would sort of do it on their own, and then we would just sort of float around the room and tell them if they had questions.
Okay.
But I mean, I suppose I could read it off the screen.
I think maybe you could like go through it very quickly, just like explain what you have to do and how to do it, kind of, and give them.
Okay.
So you don't have to probably. Maybe if you want to live code certain parts, but like you start like giving them like one line and then want the rest.
Okay. Yeah. I mean, the part that you actually fill in is kind of small, so yeah, I'm just gonna make sure I pick this up.
Really straightforward, pretty concise English. Change it's probably going to kick off right. How'd you come up with that? Why did you dude, it's like great, but like why do you like it's the newest trend to decide to so you do that yeah.
You saw it. Dude, it's just so
Hi everyone. So we're going to be doing more of an interactive tutorial right now. So there is, we have prepared a notebook for you so you can follow along and do it as I'm doing it on the screen. I think this was the link for the uncompleted version, and then this is the one for the completed version if you want to look at that now or later. So sort of the purpose of this notebook is to walk you through each of the steps that we explained in the presentation. And it's sort of laid out like a web page, so it's nice and pretty to look at. So do you want me to like read off of the screen, or would you just rather read it on your own preference? No?
Give us a general overview.
Okay, general overview. So the project in this notebook is training a classifier on the iris dataset. So what the iris dataset is it's just a labeled set of 150 different flowers that fall into 3 different species. And so people measured the petals and the leaves of these flowers so that we can use machine learning to look at those measurements and automatically classify them as different types of irises. So quick aside, we're going to be using one-hot encoding. So basically what that is if we say, oh, we have a flower and it's in the Iris setosa class, instead of saying, oh, like
it is in the iris cytosa class, we're going to have a vector and just have 3 different spots on that vector, and whichever class it belongs to, that will be a 1, and the other ones will be a 0. So that is like the right answer for that particular example. And so we're just going to have one hidden layer in the network. So this is a long section on loading the data that you don't have to look at if you don't want to. Basically, okay, so basically this loads the data, and then you can see, oh, that just disappeared. Give it a sec. Okay, so we were talking about vectorization before. So in the x variable, that's all of our examples. So each example has 4 inputs, right? So it's the width and length of a petal and the width and length of a leaf for each of these flowers, and there are 150 different flowers in the data set. And then the shape of y, which is all of our answers. So there are 150 again, because 150 flowers. And then the first dimension is 3, because you have a 1 or a 0 in each of the classes, depending on whether or not it's in that class. So here's an example. So for some 5 random flowers, you can say, oh, so this is the width of a petal, this is the length of the petal, width of a leaf, and length of a leaf. And then we can see, oh, this flower belongs in the first class and does not belong to either of the second 2 classes. And then the second flower, you have measurements for the petals and the leaves, and then it belongs to the second class. So does everyone sort of understand how that's laid out? Okay, so we need to initialize our weights, as we were talking about before. So we have 2 weight matrices and 2 bias matrices. So because we have 1 hidden layer and 1 output layer, each weight matrix and bias matrix will move the whole network forward 1 layer. So I guess I'll fill this out for... Sorry. So do you guys want to look at the completed version and then complete it on your own? Or
I'm down for like just talking and going through that.
Okay, I'm just going to make sure I don't type in the wrong stuff.
So for weight 1, it would just be like NP of like n underscore x and n underscore h.
Pretty much, yeah. So
just make sure you get the dimensions right.
Yeah, that's why I'm looking it up. So so we can use numpy.random and numpy.zeros, so that just creates matrices and vectors of a certain size with either small random numbers or zeros. So does anyone want to try and figure out what the dimensions of the first weight matrix should be?
1.
Any serious guesses?
Okay, so there's 3 different sizes. So there's nx, which is the input size, and then there's nh, how many hidden nodes we have. There's ny, how many outputs we have. So
it's W1.
What's W1? So W1, you want to get the inputs and turn it into the next hidden node. So there's 2 things involved.
So you can think of it as all the lines in between the input layer and the first hidden layer. Remember we had all those circles? Yeah, it's just all of those lines. So for each neuron we have some amount of layers of input layer connecting to it. For each neuron in the deep layer, it's connected to all the neurons in the layer. That's like it's kind of a shape. I don't know if you guys are
So I'll give you guys the answer. So the purpose of W1 is to transform our input vector into the vector that resides in the first layer. So basically, you want to do create a matrix with small random values, and we want the dimensions to be nh and nx. So this matrix will have basically nh is the first dimension and x is the second dimension. So when you multiply it with x, you multiply row, column of x, row, column of x, in order to transform it and make sure the dimensions are correct. and then we want all of these to be small, right? So just times, so all of those are small now. And the first bias vector, we're content with just that starting off as 0. So so we want that dimension to simply be an h. So after our input vector has been multiplied by the weight vector for the first layer, the weight matrix C for the first layer, it'll have dimension nh instead of dimension nx. So we want the bias vector to have dimension nh as well. So,
Question.
Yeah.
So why do you have nh first as opposed to nx?
So when you do vector multiplication, the dimensions and order of your matrices like really matter. So if you have, say you're multiplying weight matrix and then the input vector is the second argument. So basically how you multiply is you do one row of the weight matrix and then the column of the x. So you can imagine you want this row to be the same length as the column of the x. So this dimension needs to be the same length as x, and then this one will be the amount of nodes you want to have. Okay. So that also applies that, and then we need to again update the dimensions y and h.
Just one more question, because I didn't hear it while you mentioned it. Why are we multiplying it by 0.01?
Oh, it just makes them all very small.
Okay.
Yeah, so we want to start off with small weights because it's just easier to train.
So yeah.
Also, you know the reason why we have random instead of just zeros.
Because you want to have the attention dispersed, just like this.
Yep.
Why do you want to make it spinning? Why do you want to make it
spinning? So, sort of through practice, researchers have just found that it's easier to sort of get the weights where you want them to if you start from small values. Because, and also generally, you want smaller weights because it results in a more stable model and less, like if you extrapolate the model, it won't have some weird output because some weight is really large. So just sort of through practice, people have found that this works better if you start small.
You don't want your weights to be towards one extreme or the other extreme. So the angle is like you want the weights to have something towards 1 or trying to 0 or turn negative 1. But 0 is the middle ground between negative 1 and 1. So you want to have it close to around 0, but with some randomness. So like,
wait, I thought we had this random function. So it's 0.
Well, some weights can still turn out to be 0, so those would be 0 out in some cases. So yeah, so in ReLU, it's like some things, some features would cause the activation function to turn 0 because
what do you mean to turn 0?
Because if you feed in something, like you feed in an input, and then so this, if you have like a negative weight value, like if you have like a previous feature that was negative, and then you multiply it by a negative weight value, you get a positive weight.
Right.
So that would be some kind of feature that would turn on the activation function because it's more than 0.
Right.
But if you have some positive value that gets fed into the weights, and then that the activation function turns off by having it 0. So also another reason for having that, because when you take a weighted combination, you're not dealing with just one weight, you're dealing with multiple others. So something could be just a negative feature. Like you don't want, this is a negative example, you don't want that to have an output. So like, since you have other like activations to counteract that negativeness, so you could have positive weights that counteracts the negative weights. So that gives you a positive output state.
Because I assume once you hit the negative, it's automatically 0. It's turned off, right? So whether you return this value, whether you make this W1 large or small, as long as you hit this negative ground, it's going to be 0. It doesn't matter, right? I guess probably the only point that I would feel probably it makes sense is when you choose when this value is hitting on the positive ground. What she just said, if it's too large, too unstable or something.
Yeah, we have really large problem. They'll just have a really large gradient going backwards, and so then it just.
Well, not with.
But yeah, I feel like there's some loss ones we end up with that X being like that. But really, does solve a lot of these problems, which is why it's used, and why this is like a harder conversation that we're having. You know, when you talk about sigma and things like that, that's where these were first started with, and then that changed. So.
Okay, cool.
So there's a reason that's what people.
Yeah. I'm with you now.
Okay, so does everyone understand this function at least? Yes? Okay. So we can run that. And then the next step is forward propagation. So, as we mentioned before, I'll just read this here. Forward propagation computes the probabilities of a certain example belonging to each class, and each prediction is between 0 and 1. So basically, what we want to predict, remember the y values from before where there were 2 zeros and 1 1, and depending on where the 1 is, that's the class that the certain example belonged to. So basically, we want to try and compute something that's similar to that. So we want to get sort of an output y vector where the classes that the flower is not are close to 0, and the classes that the flower is close to 1. So that's sort of our goal. So the structure, the network is basically we have an input x, and x is an nx dimensional column vector. So in this example, it's going to be a 4-dimensional column vector, because remember we have 4 measurements for each of the flowers. So the first transformation, we multiply it by the weight matrix and add the bias, and we label that as z1. So then z1 is going to be an nh dimensional vector. So do you sort of understand why the amount of dimensions changed with that multiplication? Okay. So then after that, we have the application function. So this just operates element-wise, really. So the dimension stays the same. So here we're using the tanh activation. And we have our second transformation, similar to the first. And now our output of that is an ny dimensional vector. So can anyone guess the dimensions of W2? Just a quick quiz. Any guesses on what the dimensions would be /y?
NH by NY?
Yeah, I think it is. Yep, got it right. Good job. So then, after we have that, we apply the sigmoid activation function. Again, that operates element-wise. And remember, as we were saying before, what the sigmoid function does is it squeezes your output between 0 and 1. So basically, now all of our output, our 3 output in the case of the flowers, are between 0 and 1, and hopefully close to 1 if it's the correct class, and close to 0 if it's not the correct class. So really, A2 equals our predictions. So once we get to A2, we use those as our predictions. So, another clause here. So if we do this separately, for every single example, we have a for loop. We just have to do every one sequentially. That takes a really long time. We don't want it to take a long time. So that's where vectorization comes in. So instead of doing it one at a time, we say, oh, our input vector, instead of just being a simple column vector, it's now a matrix, right? So we sort of operate on each of the examples at the same time through matrix multiplication. So can implement that here. So we have all of our parameters. So z1 is going to be, just want to take the dot product of the first weight layer and x, and then add the bias, right? So take the dot product w1 and x, and then we want to add the bias. And then for A1,
No underscore.
did I not?
There's no underscore.
Oh,
B1.
thank you. Okay, so remember for A1, if we look up here, we said we want A1 to be the activation, so we just pass it through the hyperbolic tangent function. So we just say that is pi dot just take the element-wise 10H, and then Z2, we want that to be A1, so this multiplied by the second weight matrix plus the second bias. So we do dot product W2 and A1, and then we add the second bias. Does everyone understand so far? Okay. And then for the final output, we just have, we put it through the sigmoid function. Pretty simple. And then that's pretty much our output. So A2 and Y hat are the same thing. So short aside, people usually say Y hat to mean the predicted values and just Y to mean the actual values. So that's the notation that we're using here. And I think I typed that correctly. Yeah, so you can run that. So the next step is to compute the cost. So the cost function we choose to use is the logarithmic loss. So basically, the values we're dealing with, we want to predict 1 or 0, right? And our correct answers are 1 or 0. So let's say, pretend we are predicting the value for a class, but it's the wrong class, right? So we predict something close to a 1, but then the actual answer is close to a 0. So we say, oh, if we predict 0.8, but the correct answer is actually 0, we have a large loss right here. And then in the opposite case, if we predict, if the correct answer is a 1, but we predict something close to a 0, the loss is also very high, right? So basically we can combine those two notions in this equation. And if you sort of want to intuitively understand it, so this is the first, so these two sections are the first and second graphs I show you. If the correct answer is 1, then this will evaluate to 0, and this is all 0. If the correct answer is 0, this part will evaluate to 0, and then you'll only take this side. So that sort of accounts for the correct answer being either 1 or 0. Does everyone sort of understand that, or at least intuitively? Okay, we'll go on. So we can implement that here. So the loss for each function is going to be, we're just going to implement the equation, right? So y times dot log Yes, there is a negative there. Thanks. Nope, that's... Julius, your keyboard's weird.
Sorry.
Times... Okay, so pretty much you just implement that equation, and then to get the total cost, which is the average of the losses, you just add up all the losses and divide it by the number of examples, and then that's the total cost. Okay. So then we have backward propagation. So I derived all of this out. You don't have to read through it if you don't want to. But basically, we remembered this process from before. We took the input and put it through a series of different functions. So then here, we sort of unravel all of that, right? So first, we compute the derivative with respect to W2 and B2, which are the second layer weights and biases. And then we further unravel to get all the way back to the W1 and B1, which are the first layer weights and biases. So yeah, I'm not going to type that out in this function. You can if you want to. So then the next step, pretty simple, update the weights. So we want to move basically away from the high loss and towards the low loss. So when we take a gradient, that actually points in the direction of highest slope. We don't want to go up the slope, we want to go down the slope. So we subtract the gradient times a small learning rate from each of the weights. And for example, so for W1, that would be W1 minus the learning rate times the gradient, and for the rest it's the same. So then we want to put this all together, right? So we have a function. So basically each line of the function, it's going to do this multiple times, so it iteratively updates the weights. So we're going to compute y hat and remember all of our values, so that's forward propagation, and we compute the cost. We keep track of the cost just to make sure that the cost is actually going down, and we can graph that later. Then we compute all of the gradients, and then we update the parameters in each of the functions that we implemented later. So basically, when we want to create our model, we just run this function, and it returns the parameters and then a record of all the costs when it's done. So we have a whole bunch of data, right? We have a whole bunch of data on flowers. So we don't want to use all of that to train the model. We want to save a little bit for the end. So once we've trained the model, we can check that, oh, is it predicting these other flower values correctly that it hasn't seen before? So we sort of hide a certain percentage of the data from the model to use it for testing later. So that's what the train test split is. So we just chose to use 70% for training, 30% for testing. And so you can see 70% of the 150 are in training and 30% are in testing. So then it's pretty simple to train. So we can define the number of hidden nodes right here. Pass that into our function. And then we can test it by running forward propagation on all of our testing data that we saved from earlier. And then we can see, oh, how correct was it on all of these examples we haven't seen before. So when I trained it, it was like around 92, 93% correct, which is not bad. And then we sort of evaluate this. So this will plot out how the loss decreased over each iterative training session. So that's a basic neural network. If there are other things you want to look up, you can, I guess, address each one of these if you'd like to. So how does changing the number of nodes in the hidden layer, does that increase or decrease the accuracy of the network? What do you do if you have overfitting? And that's basically where the network, it sort of remembers the wrong things about a set of examples, and so when it's shown examples it hasn't seen before, it doesn't do well on them. Regularization, and that's just generally keeping your weights small because they tend to do better. And then cross-validation is another way of computing your loss. So this notebook is online. If you went to that link earlier, you can do it for yourself. So yeah, that's sort of